Hello, this is Ryan Woodward recording for Intel's Digital Logic course. This is Lab 3, Part 4. And in this part, we were required to make a 3-memory element, D latch, D flip-flop. It's not really either of those things, but it involves a D flip-flop and a D latch. And it actually, those 3 memory elements mentioned is a gated D latch, a positive edge triggered D flip-flop, and a negative edge triggered D flip-flop. And this was a bit odd, only because we had to implement this in a behavioral. I wanted to do a structural, but there were some odd results. The behavior was weird for the circuit when I tried to do structural. And then I read the document again. It suggested to do behavioral, so I went along with this. And this is why we see a behavioral circuit with the process statement. Even though it says structural there, it is indeed behavioral. Just a quick run through of this, and I'll share my Verilog code as well. I create signals where I call it gated D latch output, positive edge D flip-flop output, and negative edge D flip-flop output. And basically we process each of the inputs. We process the clock, actually, but based upon certain things. So if the gated D latch output for this portion here it'll be assigned the value of D. If it has a rising edge, and that is the same for the positive edge. Obviously, it's rising edge or positive edge. Interchangeable names, a synonymous thing referring to. Then we assigned gated D latch output to that. And then below, if we process clock and it is a falling edge, then we assign the negative D edge D flip-flop output, the gated D latch output there. And this produces, there are instances where it actually produces an incorrect result, but for the most part, my simulation was correct, and my eventual demo was also correct. But I have a suspicion that the fact that the button is debounced gave me some issues and odd behavior. But since I'm using the switches and they are bouncy, or they are actually, I don't recall. I think they are debounced, but they are bouncy. But regardless, then at the below I assign all the outputs here: QA, QB, QC, and this little q references Q bar. But I actually don't. I have those assigned to some LEDs, but they're irrelevant. I don't care about them because as we go into the document here, we can just see that FPGA Academy has QA, QB, and QC here on this simulation diagram. And we can see similar results for me here. So QC goes high when D is high and there is a falling edge. Right on that falling edge, we can see that QC is high, and that's what occurs over here. There's a falling edge on the clock while D is high, so QC goes high. QB similarly goes high on a rising edge of the clock when D is also high. And it might be hard to see, but these are not lined up, these two right here. This D falling edge and this clock rising edge. The offset is a little bit odd. It timed kind of just perfectly to show that it looks like it's there, but it is indeed not there. I think the white space here between this dashed line and the black line shows that the best. And then finally for QA, we have D high and a rising edge on the clock. And so that's why we see that. And this simulation looks good. I'm not sure why it occurred. Well, I do actually. There's the D and the rising edge and the falling edge don't line up virtually anywhere else. So that's why we see them at the end here. But alas, this is the simulation, and I got the proper results according to their little timing diagram there. But back to the code, let's go to the Verilog portion. Again, as I always say, moving from one RTL to the other I think is incredibly easy, generally, at least for circuits that are this simple. This is fairly straightforward, so it's not much more different than going from one syntax to another. But we can see that we have the always statement to process. This is the sensitivity list here as D and clock, and then we have positive edge clock and negative edge clock here. And this produces the same results. But I won't go through all the simulation for this, but this is the Verilog portion of the lab here. And that's it for the code. Whoops. Here is a brief demo of the Lab 3 Part 4 circuit, which has 3 memory elements consisting of D latches and D flip-flops. Thank you. All right, and this is the demo for Lab 3, Part 4. It has 3 memory elements with D latches and flip-flops. Ignore these 3 LEDs. I assigned them to make sure that there were no issues processing for QA, QB, and QC, respectively, on these 3 LEDs on the right. These are Q bar A, Q bar B, and Q bar C. We have our clock on the end with this switch, and then we have D, which is this final switch on the far right here. So if we were to put D up and clock that, what we should see is QA go high. And we do, but oddly enough, we don't see QB go high, which is a little weird. But we'll flip that to high. We'll show that QA goes high. And on the falling edge here, when we flip the clock down, QC will go high. And that corresponds to our simulation and the timing diagram from the lab document. And once again, once we clock this high, we'll get QB to go high as well. Oddly enough, it doesn't do it on the first one. There's probably something up in the synthesis of the code, perhaps some odd behavior going on there. But we do have the results we need, essentially, with QA and QB going high on a rising edge clock from 0 to 1, and then we have QC, this far LED, go high on a falling edge clock from 1 to 0 over here on this switch. All right, and that's it.